Our first problem is problem 11. So it is about a deck of cards. Still we have a deck of 52 cards representing 13 rings and 4 suits. 13 rings or 4 suits. That is, a card is a pair of a ring and a suit, and these rings range from 2 to 10, from jack to ace. Okay. So we are interested in 6 card hands. So we're interested in 6 card hands. So what is the number, or what is the overall number of 6 card hands? What is the 6 card hand? That is a hand, a subset, a part of our deck which contains exactly 6 distinct cards. How many 6 card hands do we have?
54, choose 6.
Exactly. And now we're interested in the number x of such 6 card hands that include a card of each suit. A card of each suit. So we are interested in some set capital X. So it consists of all such hands where there is a card of diamonds, a card of hearts, a card of clubs, a card of spades. Something like that, say. 2 hearts, jack of diamonds, ace of spades, and say queen of diamonds.
Извините, а можно вопрос задать?
Yeah.
А мы можем оставлять ответ в виде choice?
Of course. There is no need to compute these numbers to their decimal values.
Нет, я говорю, например, когда choice 1 минус второй choice, например, choice общих карт минус choice карт, у которых буквы вместо цифр. Вот. Можем мы как-то не приводить к одному знаменателю, там, не сокращать, а просто ставить в виде choice'ов?
I haven't exactly got your question.
Ну, на прошлом семинаре некоторые задачи мы решали по типу того, что мы берем общее количество комбинаций, вычитаем из них те, которые нам не подходят, и мы получаем количество комбинаций, которые нам подходят. Например, нам нужны все комбинации.
I see. Sometimes we are counting the elements of the complement of the set of our set of interest. Yes, and what of it?
Ну, вот мы можем не расписывать, не сокращать, а просто оставить больший choice минус меньший choice.
Of course, you can give your answers an arithmetical expression, including addition, subtraction, something like that.
Понял, спасибо. Thank you.
Okay, but nevertheless, how many hands contain a card of each suit? So there must be a heart, a diamond, a spade, and a club there.
The sum of choices, like choice.
What do you mean by the sum of choices?
It's like we have 4 choices which are которые ответственны за 4 масти, а 2 других чойса — это просто любая карта. То есть у нас первый чойс — это 4 из 13 плюс чойс 4 из 13, плюс чойс 4 из 13, плюс чойс 4 из 13. И
Are you sure you should add them together? So
ну,
it is something strange. According to you, you want something like that. 13 choose 4 multiplied by 4.
no, yeah, something like that, because every choice will be, я не знаю, как сказать, ответственный for each suit, like corresponds to each suit. Like first choice is correspond to heart, the second choice is correspond to romb и так далее. And after
But
that,
excuse me, are you going to choose 4 hearts? You need just one, maybe.
sorry, it's my mistake. Yeah, one.
So you want to choose a heart, and what? What then?
After that, I want to choose, ну, крести, пики и черви были.
A club, a spade,
Yeah,
and a
yeah,
heart card. But
yeah.
what should you do with these numbers? That is, this is 13.
Multiply, yeah.
Multiply.
Yeah.
So one idea, one obvious idea is as follows. So let us encode our hand. Let us encode our hand with the following information. So we shall describe it the following way. The card of diamonds here, the card of hearts here, of spades, and of clubs.
Yes, but after that, we want to say that we have 2 cards.
And then we can take a subset of 2 additional cards.
Mm-hmm.
2 additional cards. So it is a subset of how many?
52 minus 4.
That is a subset of 48 cards. Yeah.
Yeah.
So how many such tuples do we have?
Choice 1 from 13 in the first
Of
part.
course, there are 13 to the power of 4 multiplied by 48 choose 2. Yeah.
Yeah.
But is it really a bijection? I mean, this correspondence. Is this tuple really uniquely describes our hand? Is it the case that our hands are in one-to-one correspondence with such tuples? No, in fact, it is not so. It is not a bijection. Let us see. Look, assume we consider this particular hand. Yeah. Here it is. Here we have 2 of hearts, yeah? Jack of diamonds, ace of spades, queen of clubs, 3 of diamonds, and 6 of hearts. It is a hand from our set of interest. Do you agree?
Yeah.
But look, it corresponds to at least 2. It corresponds to at least 2 tuples of this kind. Okay, the first tuple will be as follows. So we need a card of of diamonds. So the problem is with this Z article. So the choice of the card of diamonds here is not unique. So you can describe it this way. Jack of diamonds, then we need a card of hearts, let it be two of hearts, a card of spades, let it be ace of spades, then say queen of hearts, and also we have two remaining cards, three of diamonds and six of hearts.
May,
This
may,
is one
may,
way. This is one way to describe this hand, but we can easily, for example, swap this two.
yeah.
Uh-huh.
May I give my answer? Like, we have to write not the choice 1 from 13. Maybe we should write choice 1 from 52 multiplied by choice 1 from 52 minus 13 and so on. No? It's like for each choice мы будем убирать карты этой масти. У нас получается каждый раз, вот мы взяли одну карту любой масти, любую, и сразу эту масть как бы выгребли убрали из нашей колоды.
But it is not correct, because in principle you can have, and in fact you must have, more than one card in at least one suit. For your hand consists of 6 cards, but you have just 4 suits. According to the pigeonhole principle, there will be a suit wherefrom you shall draw more than one card. Is it clear?
Mm-hmm.
So you need some new idea. Okay. This naive approach just doesn't work, because there are more tuples of this kind than we have hands we are interested in. But
Okay.
let us consider something else. First of all, let us answer the following question. How many, in general, how many cards can we take from each of the suits?
13.
No. I mean our hand. Assume
From 1
that
to 2?
H is a hand that consists a card of that contains a card of every suit. How many cards from every suit can H contain?
From 1 to 2.
From 1 to 2, but not all combinations are possible. And moreover, it is possible to have 3 cards in one suit. So in principle, in general, we have 6 cards. How can they be distributed among our suits? So the following equation must hold true. 6 must equal the sum of the number of diamonds, yeah, plus the number of hearts, plus the number of spades, plus the number of clubs. Do you agree?
Yes.
And every such number must be greater than 0. How many ways we have to solve this constraint? In fact, quite a lot. But what if we abstract from the particular suit we take? So in principle, we have just 2 situations. We either have a suit with 3 cards, and if we have a suit with 3 cards, how many cards we have drawn from every other suit?
By one from each suit.
Exactly. So we have two situations. Clearly, we cannot have four or more cards from any suit. Do you agree?
Yes.
So at most, we can have three cards. And if we have three cards in one suit, we necessarily have one card per every remaining suit. Is it clear?
Yeah.
Okay. Can we have less than two cards in all the suits?
No.
No, because this way we would obtain just four cards. So there must be a suit with two cards. If we have no suit with three cards, there must be a suit with two cards. Let us consider this suit. So we have how many cards remaining? Four cards to be distributed among three suits. Which distributions are possible? Of course, taking into account our constraint that every suit contains at least one card. Can we have all ones?
No.
Can we have three?
No.
So there must be a suit with exactly two cards. But then the two remaining suits must contain one card each. So we have just proved that there are just two situations. Is it clear?
Yes.
But the problem here is that this distribution is, I'd say, unlabeled. Unlabeled. What do I mean? That means that we do not know which suit exactly contains three cards. So it is some suit 1. This is some other suit 2. And so on. Is this idea clear?
Yeah.
That means that there is some choice of these suits. For example, we can take three hearts and one card in each of the remaining suits. Or we can have three diamonds and one card in each of the remaining suits. Is this idea clear?
Yeah.
So our set X of hands of interest consists of two disjoint sets. X1 is a set corresponding to this case when we have exactly one suit with three cards and three single card suits. Is it clear?
Yeah.
And X2 corresponds to the second case. As these cases are mutually exclusive, by the rule of sum, we obtain that the number of suits X equals the cardinality of X1 plus the cardinality of X2. Yep. Is it clear?
Yeah.
So, how many suits of this type do we have? Not suits, excuse me, but hands. How many hands of this type?
Choice 3 from 52. But
Why?
uh,
You should give some argument in support of your number.
okay. We have to take three cards of the same suit
Or
from
which
the.
suit? Or which suit? Or which
We are
suit?
not interested in.
We should, first of all, at first, we have to choose this very suit. Yep.
But it's like
How many ways are there to choose a suit with three cards?
4 ways for suits.
Four, of course, as overall we have four suits. So this is for the choice of our suit one. Do you agree?
Yes.
Now, for whatever choice of this suit, we have how many options to place some cards, to draw these three cards?
13 from 52. Like we have 13 cards of.
Choose
Uh,
13, choose 3. Or choose 13, choose 3 out of 13. Is it clear? Or not? This is the choice of 3 cards of this suit 1. Is it clear?
yes.
But we still have to choose 3 cards, 3 more cards. And these cards are, their suits are already known. Their suits are already determined. These are all the suits except suit 1. And for each of these suits, say diamonds, clubs, and spades, we need to choose 1 card for each. Yep. Is this idea clear?
Yeah.
So we should multiply it by 13 to the power 3. Why to the power? Because here we have an ordered tuple. It is important whether we take jack of spades or queen of spades. Is it clear?
Yes.
Or better, jack of spades or jack of clubs. So this is the choices. This stands for the choices of cards of suits from 2 to 4. Is it clear?
But actually, I have a question. Why we don't multiply 3 times more by choice 1 from 4? It's like.
From it is quite clear because look, assume that we have already chosen suit 1.
Mm-hmm.
Now we know suits 2, 3, and 4. What should we
Yeah.
choose for each of them? So now we have a function. In fact, we have a function. This function maps suit 2, which is already known, or better, not suit 2 is known. I see your question. Your question is like, why don't we want to choose suit 2? It is not necessary. We know this whole set. It is not important what is first, what is second, what is last here. They are now they are labeled. Is it clear?
Yeah.
So we need a function. We need a function that would assign a card to each of these suits. Is it clear?
Yeah, I understand. And in the second case, we have to write 2 choice 1 from. one choice one from 4, and the
Exactly.
second.
Now,
Yeah, I get it.
we have the following type of our hand, the following distribution. Now our hand is partitioned another way. So still we have 6 cards, but now we have 2 cards in one suit, 2 cards in suit 2, and 1 card in each of the suits, suit 3 and suit 4. Now we should choose what?
We have to choose 2 suits.
2 suits, exactly, not each of them. Their order doesn't matter. It doesn't matter whether we have 2 cards in hearts and diamonds or in diamonds and hearts. Is it clear?
Yes.
We should choose an unordered combination that is a set of two suits. Two suits. We choose them collectively, both of them as a subset. Now, for each of them, now they are specified. Now our suits are labeled. For each of them, we must take how many cards?
2 from 14 in the power 2.
To the power 2, exactly. Yeah. And we still have 2 more suits with certain options for each. Is it clear?
Yeah.
This is the answer. And if you do some computing, you may find out that this number, the resulting number, is substantially smaller than this one. Because here, this way, you are counting one hand multiple times. But this sum is quite a great deal smaller. Is it clear?
Yes.
Okay. Now let us continue the line of this labeled partitioning of a set. Let us solve another problem. Consider the word abracadabra. It is important here that we have multiple occurrences of one letter. Is it clear? Multiple occurrences of one letter. Say, here we have 5 occurrences of A.
Yes.
And how many words can we obtain via rearranging letters here? What is the number of words that may result from rearranging? From rearranging letters in our word abracadabra. We need a model. What do you think? How many words can we obtain? How many ways in general do we have to rearrange letters?
N factorial.
What is n?
Number of letters. Unique letters.
Really? No.
Like we may have a word like from 2 similar letters. So the length of our words starts from 1 and finish to 11.
So we have 11 letters.
Yeah.
We
have 11 types of words. Like the first type.
We have 5 or how many? Abra, 1, 2, 3, 4, 5. Yeah.
Yeah.
we have 5 letter types, but 11 letters. So in principle, we have 11 factorial permutations, but not every permutation changes the word. Here lies the problem. How can we solve it?
Divide by the number of similar letters factorial.
Of course, but why does it work? It's true. So the answer you propose, as far as I can understand, is something like that. Let us consider all possible permutations, and then look. For every permutation, if we change just the order of a's, it will not matter. Is it clear?
Yes.
So the number of permutations that matter is 5 factorial times less than the entire number. At least this many times less. But still we have, for every permutation, we have how many ways to safely rearrange letter B occurrences. Two ways. So we should divide it by 2. What else?
For R is also 2.
What about all the other letters?
C and D,
C and D have unique occurrence, so we may divide it by 1 factorial. So this is the proposed answer. Of course, you can indeed prove that this is correct, but let us consider another argument to support this answer. Let us model our word as a function. Now, we shall easily solve this problem of multiple copies of one letter. Let us model words as functions. Which functions? Functions from positions to letters. Is this idea clear?
Yeah.
So this very word, let us call it, say, F1. This very word will be which function? That maps 1 where to? To A. Maps 2 to
B.
B. Maps 3 to R. Maps 4 to still A, and so on. Is this idea clear?
Yes.
But not every function corresponds to a word we can obtain from rearranging. What is preserved under rearranging? What is preserved? It is quite obvious. What is preserved? Что остается тем же самым после перестановки?
Number of letters.
Of occurrences. Количество вхождений каждой буквы, количество ее копий. Is it clear?
Yes.
This is the main idea. This is the main idea. So every function or every word that results from rearranging has the following properties. So let us consider functions. Let us consider all the functions from how many positions? By the way, how many positions do we have?
11.
11. Let us consider all the functions from 11 positions to our letters. Which letters do we have, by the way, in this word?
A, B, C, D, R.
A, B, C, D, R. Does everybody agree? Let us consider just those functions which take, say, A, which take A exactly 5 times. Is it clear?
Yeah.
F takes B how many times?
2 times.
2 times. F takes C how many times?
1.
What about D?
Also 1.
F takes D exactly 1 time. And F takes R how many times?
2 times.
2 times. Just these functions correspond to the words we may in principle obtain through rearranging. Is this idea clear?
Yeah.
By the way, if you wish, you can make this condition a little bit more formal. This is equivalent to the following. The number of positions where A is taken is 5, or the cardinality of the preimage of the singleton of A equals 5, but it doesn't matter much. Is it clear? So how can one describe these functions, this set of functions? The main idea here is that we can describe these functions as labeled partitions of the set of positions. Look, every such function is uniquely described by specifying where, at which particular positions it takes A. Is it clear?
Yes.
How many positions should we reserve for A?
5.
5. And then we must specify what?
B, C, D, and
2 positions for B.
E.
And then
1 for C.
1 for C,
1 for D, and 2
1 for D, and 2
for R.
for R. Is it clear? It is labeled. The labels are these letters. Labeled partitioning of our set 11 underlined. Is it clear? Is this idea clear?
Yeah.
So how many partitions are possible? It is quite easy to count them. For every such partition, we have to specify 5 points where we will have A. How many ways exist to do so? Isn't it so? It is a choice for 5 positions for A. Isn't that clear? Ladies and gentlemen, isn't it clear?
Yes.
What's next? Assume we have chosen 5 positions for A. What should we do next?
Multiply it by how we can choose B.
Choose 2 positions for B, but out of how many?
6.
11 minus 5. Everything except those positions reserved for A. Is it clear?
Yes.
What is next?
Choice 1 from 11 minus 5 minus 2.
11 minus 5 minus 2. This is for C. For D.
Choose 1 from 11 minus 5 minus 2 minus 2. Minus 2 minus 1. Sorry.
Minus 1. And what will be the last one? For R.
Choice from 2 from 11 minus.
Choose 2 from 11 minus 5 minus 2 minus 1. Do you agree?
Yes.
And this number equals what? 11 choose 5, 6 choose 2. What's next?
1 from 4.
4. 4 choose 1,
4 choose 1.
3 choose 1, 2 choose 2. Is it clear?
Yes.
Aha! And now let us rewrite it via factorial form. Why is the factorial formula? You know, n choose k equals n factorial over n minus k factorial over k factorial. So what would we obtain? 11 factorial over
6 factorial.
5 factorial and 6 factorial. And here we would obtain what? 6 factorial, 2, 4. Here, 4,
1, 3.
1, 3. Here, 3,
1, 2.
1, 2. And the last factor? 2, 0, 2. Oh, excuse me. 2, 2, 0. Do you agree?
Yeah.
And look, here we have something interesting. 6 factorial is cancelled out. The same for 4 factorial, the same for 3 factorial, the same for 2 factorial, and this is, of course, just 1. And we obtain what? 11 factorial over 5 factorial over 2 factorial over 1 factorial over 2 factorial. Ha! This is exactly the same we had obtained previously from our intuitive argument. Is it clear?
Yes.
And more abstractly, it is a number of labeled partitions when of specified sizes. When we're interested in how many ways are here to partition, to split our set into pieces, into labeled pieces, that is, it is important whether we have 5 elements for A or for B. Into labeled pieces of fixed size. Is this idea clear?
Yeah.
It is also known as multinomial coefficient. Like C is known as binomial coefficient. It is known as multinomial coefficient. What is the main idea behind that? It is as follows. Look, consider the following expression: x1 plus x2 and so on, plus xk to the power n. Look, what is the coefficient? What is the coefficient we will have at x1 to the power m1, x2 to the power m2, and so on, xk to the power mk? If we expand it, which coefficient will we have? If we expand it, first of all, can you say something interesting about these powers, m1, m2, mk? What should we obtain? After all, this is the product of n copies of this sum. Is it clear?
Yeah.
So what should be true for these m's, given our coefficient is not zero? Isn't it obvious?
No, I have some problems with understanding.
Okay, let us consider an example. K equals 3. N equals, say, 3. X plus Y plus Z to the power 3. Look, can we have here the following summand x? Can we have x in
No, we can't.
y?
Like we have
X that is
two different
x to the
cases.
power 1. Can we have x to the power 1?
No. We have two cases. Yeah, two cases. We may have x to the power 2 or x multiplied by y or that.
Not
So,
y, but y.
Why
X to the
was that?
power y has coefficient 0 here.
Yeah.
It is absent.
Yeah.
What about x to the power x squared? We have x squared. How can we obtain x squared? That means that we
No.
have taken two
can't
copies of
yeah.
x from somewhere, and then we have taken 1, but there was no 1.
Yeah, I understand.
So here we have still 0. But nevertheless, it is possible to obtain x cubed.
By taking x from each из каждой скобки.
From each bracket, we should take 1 copy of x. So how many ways are here to do so?
Only one.
Just 1. So the coefficient will be 1. Is it clear?
Yeah, I understand.
Can we have x squared multiplied by y?
Yes, we can.
How many ways are here to obtain it?
3.
Of course, there are 3 ways, because we can take y from the third bracket. Another way is to take a y from the second bracket and then x from the remaining 2. Is it clear?
Yeah.
And also we can take y from the first bracket at x from the two remaining ones. So there are three ways to obtain this monomial, or in other words, 3 out of 3 choose 1. Is it clear?
Yeah.
So in general, if the sum equals 0, the if the sum does not equal n, you know, here the sum of degrees must equal 3. Is it clear?
Yeah.
So if it doesn't equal n, the coefficient is 0. But assume that it equals n. What the coefficient will be? What will it be? Okay,
Maybe the number of.
we have to obtain x1 to the power m1, yeah?
Yeah.
So we need to choose m1 bracket out of how many?
From n.
From n. These are brackets where from we take x1. Is it clear?
Yep.
But then, after having been chosen these brackets, we still need what? To choose m2 brackets out of
From
how many?
n minus 1.
N minus m1.
Yeah.
And then, is it clear?
Yeah.
And so on. So we will obtain exactly something like that. Exactly such a number. Is it clear?
Yeah.
As a result, it will be n factorial over m factorial, m1 factorial, m2 factorial, and so on up to mk factorial. When the sum of these degrees indeed equals n. Is it clear?
Yeah.
Why is it called multinomial coefficient? Because much like x1 plus x2 to the power n is known as Newton's binomial, this is known as multinomial, and the formula gives us coefficients at each monomial depending on the degrees m1, m2, mk. We can find therein. Is it clear?
Yeah.
Okay. Problem 13. How many, assume we are interested in bijections. Assume we are interested in bijections, that is permutations of the set 100 underlined. Assume we want to permute the numbers from 0 to 99. But how many bijections satisfy some additional condition? How many bijections on this set satisfy the following condition? What we obtain at the place 81, at place 81 is greater than what we have at every greater position. So look, that means that f81 is greater than what? Than f of 82, f of 83, and so on up to f of 99. How many such bijections do we have?
$19.
How many? 19. Why?
No.
Hmm.
Um,
How can we count them?
like we know that on the I think that 80, 82, and 83 have to be equal less than 18, like from 1 to 17, and we may say that it's like 18 multiplied by 18, like 18 square. No.
Of course not. Okay. Do we have any constraint on the number f of 82 or on the number at the position 82? So what do we know about this number?
It's less than
Less than the number at the position 81.
yeah.
So, for example, this number cannot be 99. So there are some constraints. Is it clear?
Yeah.
We have exactly the same constraint for the number at the position 83. Do we have any constraint at the for this number, f of 81? By the way, how many numbers do we have here? How many positions?
18.
How many?
18.
18. Here we have 18 numbers, which are pairwise distinct. Why are they pairwise distinct? Because this was a bijection. Is it clear?
Yeah.
So f of 81 must be greater than some 18 numbers. So the least possible value for this is 18. 18 is greater than 0, 1, and so on up
Yeah.
to 17. So we have quite a lot of constraints. And it is not that clear how can one solve them. Do you agree?
Yes.
But there is a very easy way to solve it. Let us consider the following question. Which numbers can occupy positions 81, 82, and 99, up to 99? Which numbers collectively can occupy all these positions? Are there any constraints? We know that f of 81 must be greater or equal than 81. 8 of 81 must be greater or equal than 18. Do you agree?
Yes.
But among 90 numbers, and here we have 90 numbers, among 90 numbers, and among 19 distinct numbers, there necessarily is a number which is greater or equal than 18. Do you agree?
Yes.
So, for example, this constraint is not necessary for, so, okay. do we have any constraint on all these numbers collectively from 81? So do we have a constraint on this set? On this set? It is the main question. What this set may be?
We can say that f of 81 less or equal than any 19.
No,
F.
this number can be whatever, starting from 18. It can be 99, for example.
So f of from 81 greater than any 19 numbers. No.
No, it is not greater than any. It must be greater than all the subsequent numbers because they are distinct. That means that our f of 81 must be greater or equal than 18. But do we have a constraint on this set? The main idea here is that we have absolutely no constraint. The main idea is as follows. This may be absolutely any subset of size 19 element subset of our set 100 underlined. Why is it so? Because if you take whatever 19 numbers, you can place the greatest among them to the first position. And then you can place all the other numbers in whatever manner. Is this idea clear? Okay. If you are not sure, please give me a 19 element subset. Give me a subset.
From 0 to 18.
From 0 to 18. Okay. It is very easy. Then I'll place 18 to the position 81, and then I'll place all the other numbers in any way. So let that be 1, 0, 5, 11, 6, 2, 3, 4, 7, 17, 14, 9, how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, what else? What have I left out? 8, what else?
По-моему.
Yeah, 12. So how many numbers do we have? And 13. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11,
Yeah.
12, 13, 14, 15, 16, 17, 18. So does this arrangement does it meet our requirement?
Yeah.
So it is possible for whatever subset of 19 elements, because the only thing you should do is to place the greatest number among this given to position 81. Is this idea clear?
Yeah.
So here we can easily construct the answer. So how many bijections do we have? Easy. This is the choice of this set. The choice of this set of elements at positions from 81 to 99. Is it clear?
Yes.
Then we shall have some freedom. Which freedom? To rearrange these numbers. How many numbers do we have?
18.
These numbers have been already chosen. Do we have any constraint on their order?
No.
So
Like-
how many ways do we have to reorder them? 18 factorial, yeah?
Yeah.
And also we still have how many numbers? Except those chosen.
81.
And also we have 81 number. Also we have 81 number, which can be reordered in this many ways. And if we do some arithmetic, we can make an interesting observation. What do we have? This is cancelled out. 18 factorial over 19 factorial. What is it?
19.
1 over 19. So what is it? It is the overall number of bijections over 19. So that means that every 19th bijection satisfies our constraint. Is it clear?
Yes.
This is the overall number of bijections over 19. So every 19 satisfies. How can we explain it intuitively? Let us consider, say, a random bijection, whatever it may mean. Look, what are the chances that f of 81 will be greater than all the remaining, all the subsequent numbers? These numbers are 1 out of 19. Why is it so? Because if we consider the last 19 numbers from f of 81 to f of 99, then one of these numbers is the greatest among them. Do you agree? They are all distinct, hence one of them is the greatest. Isn't it clear?
Yes.
But what are the chances that the greatest one will come first? If you rearrange them randomly.
1 from 19.
1 to 19. Is it clear? 1 out of 19. You have 19 numbers. One of them is the greatest. What are the chances that this greatest one will be taken first? Randomly. 1 over 19. So every 19th, on average, every 19th bijection satisfies our constraint. Is it clear?
Yes.
One could make a proof from this probabilistic argument as well. But of course, most likely in mathematics, when developing probability theory, you start from combinatorics and introduce probabilities. But in principle, the other way around is also possible. And now, let us recall what we know about binomial coefficients. I have stated a theorem about this expression, x plus y to the power n. N is a natural number and x and y are, say, arbitrary reals. So this binomial equals what? Do you remember the answer?
The sum of x plus
X to the power k multiplied by y to which power? We have
n
already,
minus k.
of course, exactly. We know that the sum of these degrees must equal n. So if the degree of x was k, then the degree of y is n minus k. And what is the coefficient here? Where k runs from 0 up to n plus 1 summand. Is it clear?
Yeah.
What if we take 1 for x and for y as well? What the result will be?
Just one.
Okay, let us compute the left-hand side. Substitute 1 for x and 1 for y. Will it be 1?
2 to the power n.
Exactly. And what about the right-hand side?
The sum of all n choose k, k runs from 0 to n.
The sum of all these numbers, which are known as binomial coefficients. You know, they occur in this binomial formula. Okay. But now let us try proving some identity, namely this one. N multiplied to 2 to the power n minus 1. This requires n to be greater or equal than 1. This equals the sum from k, or does it require? Yeah. This sum. How can we prove it? Maybe we can somehow use this identity. Any ideas, please?
Maybe we could substitute the sum of n choose k's for the 2 to the power n minus 1.
2 to the power n minus 1, but here we have just 2 to the power n. Substitute what for what?
2 to the power n minus 1 equals the sum of all c and n minus 1 choose k.
Why? Why is it so? I see your point. I see your point. This one, yeah?
Yeah.
Okay, and what of it? That's it. I agree.
And if it is multiplied by n, it won't be n choose k. It will be just not n minus 1 factorial, but n factorial in the numerator in all sum.
But you won't multiply what by n? Okay, I see your point. Probably I see your point. Now, let us multiply the both sides by n, and let us apply this formula, yeah? The formula with factorials.
Yeah. Exactly.
Interesting. Yeah. So we will obtain n multiplied by n minus 1 factorial over what? K factorial n minus 1 minus k factorial.
Yes, indeed.
But here we have some difference between our previous with our previous argument.
Yes, and if we multiply each of these elements of the sum with k factorial, we will have not k factorial in the denominator, but k minus 1 factorial in the denominator.
I see. So probably your idea may be put the following way. So clearly here we have n factorial. And now let us have here k. If we have here k, then here we'll have k. No, that's not true. That's not true. So k minus 1 factorial multiplied by k. I see. So we can have k plus 1 here, and k plus 1 factorial in the denominator, and we can rearrange it this way. Do you agree?
Yes, indeed.
But what is it? What is this product? What is it?
This is n choose k plus 1.
Multiplied by k plus 1.
Multiplied by k plus 1, yes.
It is n choose k plus 1. Exactly. Brilliant. It is almost what we need, with one distinction. Here k ranges from 0 to n, but here it ranges from 0 to n minus 1.
As we have the k plus 1 in there, we can actually substitute k prime for k plus 1. And
Yes.
then we'll
Let us rename the variable. For example, to make things easier, let us rename k plus 1 to L. K plus 1 to L. Okay. If k ranges from 0 to n minus 1, then k plus 1 will range where from? From 1 to
k. To c.
n. Look,
Yeah,
if you
yes.
substitute 0 here, you will obtain 1. If you substitute n minus 1 here, you will obtain n. Do you agree?
Yes.
But k plus 1 can be replaced by L here. And this is almost we want. But here we have one more summand. Z for k being equal 0. But this summand equals It equals 0, of course. We can rename L to K back. We can rename L back to K. And finally, we may obtain what we need. Is it clear?
Yes.
This was one proof. Brilliant. You have proved it. But interestingly enough, we can solve this problem in many other ways. One of the most striking, in my view, is the analytical proof. What if we substitute 1 for x here, 1 for y here? What will it be? X plus 1 to the power n equals such a sum. Do you agree?
Yes.
Both sides are functions of x. Both sides can be treated as functions of x. What if we differentiate these functions? What the result will be? Let us differentiate the left-hand side.
It will be n
Yeah.
x plus 1 to the power n minus 1.
Exactly. And what if we differentiate the right-hand side? For 0, there will be constant whose... So what would we obtain? This sum, yeah? Is it clear?
Yes.
What should we do next? One last step. Let us substitute 1 for x. So the result will be
n times 2 to the power n minus 1, the sum of all n choose case.
Is it clear? Look, by the way, this x to the power minus 1 plays no role because it is multiplied by 0. So everything is okay with it. So this is another proof for our statement. Is it clear?
Yes.
And now let me give the last proof, combinatorial one. Of course, there are other proofs, say by induction, but for example, let us consider all binary words, all the binary words of length n. Assume, for example, that n equals 3. Please give me all the binary words of length 3. Binary words are tuples or sequences of length n comprising zeros and ones. Which binary words do you have? Please name them. It is a sequence, ordered sequence, a tuple. Ladies and gentlemen, isn't it clear what a binary word is? Apparently you do not know what is a binary word. Двоичное слово – это последовательность упорядоченная нулей и единиц. Ladies and gentlemen, please name all the binary words of length 3.
0, 0, 0, 0, like
0, 0,
0, 0.
this one.
Yeah.
Is it of length 3?
Length, okay, length reads without the last number.
What other words do you have?
0, 0, 1, 0, 1, 0, 1, 0, 0.
It is better to place this one here.
Okay. 1, 1, 0.
1, 0, 0, 1, 0, 1, 1, 1, 0.
And 1, 1, 1.
So how many?
8.
And in general, according to the rule of product,
2 to the power 3.
2 to the power n in general.
Yeah.
Such words. And now, the question is as follows. How many how many unities do we have in these words overall, in general? Let us count them. In this case of n being equal to 3, how many unities do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have 12 unities. Is this idea clear?
Yep.
Yeah.
And how many unities do we have overall when n is arbitrary? How can we count them? We have two ways to count unities. One way is which one? Do you have any ideas after all? How can we count these unities?
Yeah.
So please.
Like we have only two numbers, 0 and 1, and it's might be clear that in a half of в половине случаев на месте будет стоять единица, а в другой половине 0, то есть неравноценно по вероятности.
Exactly. For every position, we have 3 positions. Is it clear?
Yeah.
For every position, we have as many words with 0 there as we have words with 1 here. So if we look at this table, we may obtain what? At this table, we have n positions. Do you agree?
Yeah.
And how many words do we have?
8.
2. In general.
2 to the power n.
2 to the power n words. Ha! So what is the size of this table? So we have n columns and 2 to the power n rows. Do you agree?
Yeah.
And for every position, we have as many words with 0 there as we have words with 1 there. Why? Because there is a natural bijection. Just replace 0 by 1 and vice versa. You will obtain a word from our table. So, in each column, we have exactly 1/2 of ones. Do you agree?
Yeah.
So what is the total number, what is the overall number of ones? It is 1/2 the size of our table. That is 1/2 multiplied by what? By n, by?
2 to the power n.
That is n multiplied by 2 to the power n minus 1. Do you agree?
Yeah.
And this is true for this particular case. 12 equals 3 multiplied by 2 to the power 3 minus 1. So we have obtained this number as the number of unities in this table. But can we obtain this number?
Yeah, we have to... Нам нужно найти количество разных чисел с определенными коэффициентами. То есть у нас первый коэффициент будет равен нулю, это количество цифр, состоящее только из нулей. Второй коэффициент будет равен единице и умножить на количество чисел, где есть хотя бы одна единица.
Not цифры or числа. These are tuples of words.
Yeah.
Aha, of course, right you are. Let us count separately the number of unities in words that contain exactly k unities. So we have two questions. How many words? How many words contain exactly k unities? It is the crucial question here. How many words contain exactly k unities? How many words contain of length 3 contain exactly 2 unities?
It's like how many letters we have in word.
Here you are right, but in general you won't be right. Because the main idea here is to choose 2 positions for unities out of n. Do you agree?
Yeah.
So for arbitrary k, we have n choose k words that contain exactly k unities. Because this is the number of ways to choose the positions for these unities. Is it clear?
Yeah.
But look, there are as many words with k unities. But how many unities every such word provide? How many unities does every such word provide? To the overall sum. Isn't it clear that in every word with k unities, we have k unities? Isn't it clear?
Yeah.
So we have k unities in words that contain k unities. For example, here we have 3 choose 2 multiplied by 2. Yeah, so it is 6. 1, 2, 3, 4, 5, 6. Is it clear?
Yeah.
So the overall number of unities equals k multiplied by c by n choose k, where k ranges from how many unities can we have in a Wharton principle?
3, like the maximum.
Oh no. We are considering the general case. В слове длины n может быть от 0 до n единиц. Isn't it that
Yeah.
clear? So k ranges from 0 to n.
And
Ha! So we have computed the same amount in 2 ways. Hence, the 2 resulting formulas must be equal. This is another example of the prominent double counting, when we are counting the same amount in 2 ways and then equalizing the resulting formulas. Is it clear?
yes.
This is another proof for our identity. Do you have any questions?